Welcome back to multivariate calculus. In this video, we're going to be looking at parametric surfaces. The idea of parametric surfaces is very much an analog to parametric curves we studied earlier in the course. And a lot of our vocabulary, a lot of our discussion is going to be in emphasizing those parallels. Let me get my head out of the way and we'll dive in. When we talk about a parametric curve, and I'm going to talk about a parametric curve in 2 dimensions because I think that's the easier analog to see. The value of a parametric curve was in looking at things and trying to generalize the idea of a function. Right? A function, y equals f of x, has a nice progression. Right? There is an obvious order and direction to a function following along the x-axis. If I have an arbitrary curve, I lose that. For example, if I have an ellipse, right? X squared over a squared plus y squared over b squared equals 1, just a usual ellipse. There's no order, there's no progression, there's no starting point, there's nothing that we can use to define what's happening. And so, it becomes valuable to have that vector valued function r of t equals x of t, y of t. You can parameterize the same kinds of curves that we have as arbitrary curves, but you get a definite starting point, ending point, and direction as you go about things. It can be counterclockwise, it could be clockwise, it could do other sorts of things, but it has an inherent direction. And having that inherent direction allows us to look at things a little bit more specifically than we could with the arbitrary curves that we have pretty well avoided throughout our discussion of calculus of one and several variables because there is so little we can do with them. The same thing is true on surfaces. If I have a surface z equals f of x and y, let's do this in a different color so that it stands out. The thing about a surface is that I have very clear this is what the x-axis wants to do, this is what the y-axis wants to do. And so I can raise that grid up onto the surface and be able to work with it. We looked at arbitrary surfaces. Right? Things like the sphere, x squared plus y squared plus z squared equals r squared. And a sphere will let us have a surface that does not satisfy the vertical line test or the hyperbola of one sheet, the ellipsoid, the hyperboloid of two sheets. All those things allow us to break that rule of having the vertical line test on our surface. But by doing that, we lose the orientation. And so a parametric surface Well, instead of having just one parameter, as we saw here in our function, we need two separate parameters, an x direction and a y direction. Although x and y are our coordinates, so since we can't use that, right, u and v are a common thing to use instead. And it will be a vector with components. Each of those components is itself a function of u and v. And this will allow us to get a surface like a sphere or any other surface that does not satisfy that vertical line test and come up with a way of assigning a grid to that sphere so that we can talk about coordinates happening on the surface and build up from there. So for example, let's start practicing how to visualize a surface. I'm going to go into GeoGebra and I'm going to try to graph the surface R of u and v has components 2u cosine v, 3u sine v, u squared. And I'm going to let u range from 0 to 2 and let v range from 0 to 2 pi. Typing a surface into GeoGebra is similar to typing a vector valued function or a parametric curve in, but GeoGebra is not quite so good at figuring things out and automating the process, so we have to do some of that work on our own. We need to tell GeoGebra that we are creating a surface. To create a surface, you want to type in the word surface with a capital S. And yes, the capitalization is important. And if you just start typing it in, it will pop up and it'll give you this menu that will give you a couple of different ways you can set up a surface. The one we're looking for, the parametric surface, is this third one that has expression, 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 parameter variable, start value, end value, and it keeps going off the edge of my screen. Now that we have that, we want to go in and type in our x coordinate, 2u cosine v, type in our y coordinate, 3u sine v, type in our z coordinate, u squared, and then we get to parameter variable 1. Our parameters are u and v. So we type in u for the first parameter. We had that u was between 0 and 2, so the start value is 0 and the end value is 2. Then we go to our second parameter, which we said was v. It started at 0 and it ended at 2 pi. So I type in 2 pi. And it gives us the graph of this curve. And as we look at this, you can identify that it looks like an elliptic paraboloid. And in fact, that is what we have here. We have an elliptic paraboloid. Although it's definitely getting cut off in places. So let's try to play around a little bit with the parameters and try to figure out what's happening. All right, starting off with the z coordinate, that's the easy one. Z is u squared and u goes from 0 to 2. So u squared is going to go from Well, 0 to 4. Want to stretch out a little bit more than that, so maybe we'll go from -1 to 5 or -2 to 6 in my z coordinates. In x and in y, I've got 2 times u times a trig function, 3 times u times a trig function. Well, a trig function is going to range between -1 and 1, right? Either sine or cosine, has a minimum value -1, a maximum value +1. And then u goes from 0 to 2. So the minimum value is going to be 3 times 2 times -1, -6. The maximum value is going to be 3 times 2 times +1, +6. To avoid skew, I'm going to make sure that I stay the same in my x and my y direction. So let's go into the settings menu here. Let's go to settings and let's type those things in. I want my x values to go to at least -6. Let's go -6.2. My maximum is also going to go to +6.2. I'm going to do the same thing for y. Again, I could have used something smaller. I could have used something smaller for x than for y, but keeping x and y symmetric is going to prevent me from doing anything strange as far as skewing the figure. And then we'll take z going from, I said -2 to +6. We'll stick with that. That seems like a good thing to do. While I'm in the menu, I might as well set up my labels, make sure that x is labeled as x, y is labeled as y, and z is labeled as z so I can tell what's going on. And let's close this menu. And now we can see that we have this elliptic paraboloid, but it has that hard cap on it. That's one of the advantages of parametric surfaces. Once you have set up where your extents are going to be, you know what the extents are and you can figure it out. Spin this around, get my x and y axes where I usually see them looking down, and we have some idea of the ellipse we're looking at. Bring those back around and look at this in the orientation we usually try to sketch things in. We can get a feel for what this surface looks like. Right. Unlike when we were looking at equations of surfaces as functions, or even the quadric surfaces, when we're looking at a parametric surface, it has a definitive endpoint. So you do have to make sure that you zoom out far enough to get the entire surface displayed when you're graphing this. All right, back over to my notes. There we go, back over to my notes. When we've talked about parameterization in the past, we've had a couple of different tools. We were able to parameterize things that were functions, right? If we had y equals f of x, then we were able to set up a parameterization. R of t is equal to t and f of t. And then we were able to reparameterize by multiplying the x component by various things or changing that around. Another thing that we did frequently in parameterizing was to change to polar coordinates. If I had my function that I could write as r a function of theta, then I was able to write my vector valued function r of t as r times the cosine of theta and r times the sine of theta. Right? We use that to great extent in parameterizing our circles and things like that. But in general, if we had something that had x squared plus y squared, which we could change that into r squared, and then use our polar coordinates, x equals r cosine theta, y equals r sine theta, and just replace theta with t and get one complete loop for graphing t between 0 and 2 pi. Those same tricks will work if we want to parameterize a surface. If we have a surface z equals f of x and y, we can parameterize it r of u and v, just set my x component as u, my y component as v, and then get f of u and v as the z component. It's a little bit trickier to do something in cylindrical coordinates, but we can take advantage of x equals r cosine theta, y equals r sine theta, and z equals z if we have expressions for r and theta, and maybe something like a surface of revolution where we had z equals some function of r. That gives us all the tools that we need, right? Well, if I just set my r as one of the parameters, then I get the surface is defined as u cosine of v, u sine of v, and then f of u. All right, so there is one way we can play around with cylindrical coordinates in order to get things working out. And again, 0 less than or equal to u, less than or equal to some radius that we're looking at, and 0 less than or equal to v less than or equal to 2 pi, because we use that as our circle constant. The other tool that we have at our disposal is spherical coordinates. I guess we used rho when we did spherical coordinates. I should be consistent about that. We have our conversions here for spherical coordinates. So if we had a perfect sphere, we could just set u equals theta, v equals phi, and 0 less than or equal to u less than or equal to 2 pi. And then remember that phi goes from 0 to pi. And if we have the radius as a function of angles, then that's what we need in order to write this as spherical coordinates. All right, so we can play around with a lot of things that are very analogous to what we've done before. I don't want to spend too much time looking at writing the parameterization. I want to spend time in this video in doing the parameterization. All right, and one of the easiest things to do with any function is to think about differentiation. And once again, instead of trying to think about this in detail, I'm going to think about this in analogy. The derivative of r of t, if I had that r of t was vector with components x of t, y of t, z of t, we found that we could differentiate component by component, and we got the vector with components dx dt, dy dt, and dz dt. So by analogy, if I want to take the partial derivative with respect to u of a vector valued function r of u and v, it should work the same way. I should get, I guess I should write this out. I'm assuming here that r of u and v has components x of u and v, y of u and v, and z of u and v. But if I have that, I expect the same process is going to work. I just differentiate component by component. So I will have partial of x with respect to u, partial of y with respect to u, and partial of z with respect to u. And likewise, if I want the partial with respect to v of r, that will give me the components partial x with respect to v, partial y with respect to v, and partial z with respect to v. All right, so going back to the function that I was looking at on the graph a little bit ago, let's use this tool and make sure we can make sense in how to differentiate. Again, the key here is don't overthink it. We know how to take a partial derivative and just take a partial derivative component by component. The partial of r with respect to u is going to have components. The partial of the x component with respect to u is a variable, v is a constant. But we get components 2 cosine v, 3 sine v, 2u. And then if I take the partial of r with respect to v, well, the derivative of cosine is negative of sine. The derivative of sine is cosine. And the u is constant with respect to v, so the z component, derivative of u squared with respect to v, is just 0. Right. Nothing new happening here. The notation is a little bit weird because we're combining things that we've done before, but everything is hopefully reasonable. It's the same process we saw for partial derivatives. It's the same process we saw for differentiating vector valued functions of one variable. Now we're differentiating vector valued functions of two variables. All right. Continuing to look at the same surface. When we've dealt with derivatives in the past, the first thing we look at has been tangent lines and tangent planes, and that's not going to change here. We want to find the equation of the plane tangent to the parametric curve, same curve we've been dealing with, and a particular point values u equals 1, v equals pi over 4. And if we stop and think about it for just a moment, it should make sense that partial r partial u and partial r partial v are both vectors tangent to the surface. The way that I think about this, for partial r partial u, we're looking at the change in u assuming v is constant. Well, pick a particular value of v, say v equals pi over 4. Once you have picked that value of v, your surface collapses. Instead of having two dimensions that we're caring about, it collapses down to a single one, and we've suddenly defined a path in the u direction on the surface. And we know that if we have a parametric curve, a parametric path, the derivative gives a vector pointed tangent to the curve at that point. Likewise, if we pick a specific value of u, say u equals 1, now our function of u and v turns into a function of just v. And we've picked a path going in the other direction, in the v direction. So we are looking at a path in two different directions. And we know from our discussion of planes from previous videos that if we have a vector that is tangent to the surface in one direction and another vector that is tangent to the surface in a different direction, that we are looking for the plane that contains those two vectors, and that will give us our tangent plane. We can figure out how to write the equation of a plane by taking the cross product of the two vectors. Let me get my head back out of the way and let's go through all of those calculations. We've already taken these derivatives. We know that partial r partial u has components 2 cosine v, 3 sine v, 2v, and we want to evaluate that at the point 1 pi over 4, right? Cosine of pi over 4 is square root of 2 over 2, multiply that by 2, and we just get square root of 2. Then we'll get 3 square root of 2 over 2, and in the last one, it's a u there. 2 times 1 is 2. And similarly, partial r partial v, we saw before, was negative 2u sine v, 3u cosine v, and 0. And if we evaluate that, at that point 1 pi over 4, we'll get negative root 2, we will get 3 root 2 over 2, and we'll get 0. Before I scroll too far, I also am going to need to calculate the point itself. R of 1 and pi over 4 is going to be 2 times 1 times cosine of pi over 4, which is still square root of 2. Then we're going to have 3 times 1 times sine of pi over 4, which is going to still be 3 root 2 over 2. And then we're going to have 1 squared, which is 1. All right, so we will need all 3 of those things in order to figure out what's happening. To write the equation of a plane, we need the normal vector, which we can find as the cross product of the 2 vectors that are in the plane. So we're going to have some normal vector n, which will be partial of r with respect to u cross with partial of r with respect to v. And I'll set that up using matrix notation. I, j, and k across the top row. The second row is the components of partial of r with respect to u, which were root 2, 3 root 2 over 2, and 2. The second row will be partial of r with respect to v, which in this case was negative root 2, 3 root 2 over 2, and 0. Right. Using cofactor expansion, eliminate the row and column with I, leaves us with 3 root 2 over 2, 3 root 2 over 2, 0. Eliminate the row and column with j, leaves us with root 2, 2, negative root 2, 0. And eliminate the row and column with k gives us root 2, 3 root 2 over 2, negative root 2, 3 root 2 over 2. And then main diagonal minus off diagonal is going to be 0 minus 3 root 2, right? 3 root 2 over 2 times 2. 2's cancel out, and we're left with 3 root 2. And then we'll have 0 minus negative 2 root 2. And then we will have, all right, here's where things get a little bit complicated. I'm going to not write out as much as I maybe should. I've got root 2 times root 2, which is 2. Divide by 2, which cancel each other out, giving me 3 for the first term. And then the same thing happens on the second, on the off diagonal, except we have that negative. So I get 3 minus negative 3. All right, so all told, my normal vector here is going to be negative 3 root 2, negative 2 root 2, 6. And then the equation of a plane, I take my normal vector, I dot it with the difference of my arbitrary vector x, y, z minus r naught, the vector pointing to where we actually want to draw, which we did figure out that was r of u equals 1, v equals pi over 4. So we have here negative 3 root 2, negative 2 root 2, 6, dot with x minus the x component. If I scroll way up, this is where we're looking at. The x component root 2, y component 3 root 2 over 2, z component 1. So we've got x minus root 2, y minus 3 root 2 over 2, and z minus 1. And so we just multiply that together. So we'll get negative 3 root 2 times x minus root 2 minus 2 root 2 times y minus 3 root 2 over 2 plus 6 times z minus 1 equals 0. And that's the equation of the plane. All right. Hopefully a nice review of some things that we've talked about before. Again, not a lot is incredibly new here. We have looked at vector valued functions of one variable, curves in space, parametric curves. We've taken the derivative of those. We've found tangent lines of those. We've looked at surfaces defined by equation, and especially surfaces defined by functions, z equals f of x and y, and we found the partial derivatives, and we found the equations of tangent planes. I'm just bringing all of that together in one place. Of all of this, I suspect that the thing that you need the most practice with is going to be writing the equation of the surface in the first place, so I would like to go there. I would like you to spend a little bit of time thinking about how to write the parameterization of the surface of the sphere given as x squared plus y squared plus z squared equals 25. Right, take a couple of minutes, see what you can come up with there, and I'll see you in the next video.